Hey guys, so in this video I'm going to quickly show you how to create your Joukowski Airfoil and use the code that I posted online to create an input file for Xfoil or XFLR5 and generate CL versus alpha curve. So it's very simple. So let me quickly walk you through what the different steps. So this is the homework 8. You should have your code by now, right, where you generated your Joukowski Airfoil. So one thing that I would recommend right away is that in the last homework you might have used a naught and b naught value as negative 0.1 and 0.2. But in this homework, to create a thin airfoil, we might need to reduce your a naught and b naught value so that your Xfoil or XFLR5 doesn't crash. It happened, so I learned the hard way. So you reduce your a naught b naught. I recommend in the order of 0.1, 0.2, 0.3, somewhere in that order. So you can either create, I would recommend creating cambered airfoil, but you can play around with symmetrical airfoil as well. So here in my code, I set a naught and b naught value as 0.04 or minus 0.04 and b naught as 0.02. So I'm just going to run it to create the file. So one thing that I did in my homework 8 is that I put in this command right here to save my airfoil. So here I'm creating, so if you see here, this is my theta, define theta, and then I define my x and r, and then I use Joukowski transformation to get the airfoil, and from there I'm actually storing the airfoil value, right? So, and then by using this command called airfoil.mat slash airfoil, I'm saving my airfoil coordinates as a mat file. So once you run this code, you should see an airfoil.mat file in your folder. So now open the file that I posted online on homework 9 named write input file. Okay, so you can actually go through the file, and I commented on it. I divided it into different sections so that you know what's going on in each and every section. So basically, what I did is in the step I normalized the airfoil. So if you look at your airfoil, it actually goes from negative 1 point something to positive 1. So for Xfoil and XFLR5 to recognize the airfoil, the entire airfoil has to be between 0 and 1. So the leading edge has to be in 0 and trailing edge has to be 1. So that's kind of what I'm doing in this section. And then I'm interpolating the airfoil coordinates so that I can get the x and y values at certain intervals that I want. So it's one of the for Xfoil and XFLR5 you need that. So and I refine the coordinates a little bit by basically you have the same interpolation, and then I arrange them so that you can back out or download the data file pretty easily. But you don't have to do anything in the code. What I did here is that I wrote a command called dlm write where you can actually run the program and save the airfoil coordinates as a dat file. So here, you can name your own airfoil because it's not an accessory, so there's no nomenclature for naming Joukowski airfoils. So you can pretty much make any name that you want. It's your airfoil. It's you. You're the one who created it. So be creative, I guess. Right. So what you can do is once you run it, right, it takes in the airfoil coordinate, and then in the code actually plots the actual coordinates from homework 8 and the refined coordinates. So you have to double check that you get the same shape as your airfoil coordinates from homework 8, because sometimes you might see the leading edge not being totally resolved, or sometimes you might see a blunt edge. So you got to be careful about that. I made sure the code to be universal no matter how many data points you use or what value of a naught and b naught you use. You should get the code should work. But in special circumstances, if it doesn't work, then just let me know. But as you can see, your coordinates of the refined airfoil, if it's, x-axis go all the way from 0 to 1. So now I think we are all ready to use the Xfoil or XFLR5. So as you can see in my folder, the code actually created a file called Joukowski 33. Think I saved 33 because I was using 0.03 and 0.03 as my A0 and B0 values. So that's all we need for XFLR5. So what I'm going to do now is I'm going to open XFLR5. So let me quickly go to downloads. So I'm using Mac. Your Windows will also work. So you just have to download XFLR5 for Windows. So what I'm going to do now is I'm going to go to File. I'm going to open my data file. So the data that I just created is in my MATLAB folder. So here it is, Joukowski 3388, 33.dat. So I'm going to double click it and I'm going to select this. So here, as you can see, that's the airfoil that I just created, right? So you can scroll to change the size. But before you begin analyzing, you might need to refine or add more data points to the airfoil, because as you can see in the leading edge, it's not very refined, right? So for that, you can actually do that in XFLR5. So go to File and do a direct foil design. Okay, make sure that this box is checked and go to Foil and do Refine Globally. All right, so here is where you control the number of panels. Now, we haven't talked about panel methods yet. So, after we finish our thin airfoil theory, we're going to switch gears and we'll talk about panel methods. That's basically what XFLR5 and Xfoil is doing. So for panel methods, I'm just gonna put a number of panels to 40, and then you can just leave everything the way it is and click OK. I'm just gonna click OK, and then yes, all right. Now you can see that the airfoil has been refined, both leading edge and trailing edge. Now we are actually ready to do the analysis. So I'm gonna go direct, Xfoil direct analysis. So here, you see the airfoil. Right now, I'm going to go to analysis. I'm going to do define analysis. So as I mentioned in class, you can pretty much set any Reynolds number you want. So I'm just going to click OK. Now I have, I'm going to run a sequence from -4 to 10 in increments of 1. Make sure the viscous is ticked. Okay, and for some reason XFLR5 doesn't produce any data when you uncheck this mark. So make sure this, you check viscous. So when you plot viscous, when you run viscous analysis, it actually calculates both viscous and Inviscid code, right? Now all you have to do is just click analyze. So as you can see, so before we get to the data, I don't know if I can pull up the convergence history. So basically what you need to do is you have to make sure that the data, the pop-up box that you just saw shows all the values are converged, okay? So if the value is not converged, then you won't see that angle of attack in this list, okay? So now if you go to your file right here, right? If you just click this, you will be able to see CL versus CD. You'll be able to see CL versus alpha. So basically, this is exactly what we need. Okay. So what you're going to do is, you can export this result, where just right click it. You have current polar, and then you can export it. So once you export it, I'm just going to save that in desktop. Okay. So it's already there. All right. Now, if you go to your desktop, right, here you can see minus alpha, angle of attack, and CL, right? So basically, this is what you need, right? You plot, and then you copy and paste this to Excel, and then you plot alpha versus CL, and you need to plot 2 pi, elliptic curve slope of 2 pi, and see, if it matches well with what you have in here. Okay, or one thing that you could do is you could actually calculate the slope of this line and see what you get. Okay, so the other cool thing that you can do here, in this program XFLR5, is that if you go to your CP graph, let me quickly adjust this so that can do is I'm just going to set this to 0 to 1. It's my card, and I'm just going to set this, say, negative. So it might go to -2 or 3. I'm just going to set to -3, and the maximum, as you know, CP starts at 1, right? So I'm just going to apply, and then yeah, that's actually good. So I'm just going to do 0.1, apply, and -3 to 1, and 0.5. All right, now you can actually see the plot, right? So I can click this, you actually see the pressure distribution of your airfoil. It's pretty neat, right? This is the airfoil that you created, and it's something about it, it's for, to me at least, it's very interesting to see all this. It's the airfoil that you created, you own this, so it's I like it. So here you can actually see the distribution of pressure and the corresponding CP variation. So for any angles of attack, you can even make it animate. Just pick that, and then it will do the animation for you to see what happens as the angle of attack is changing, right? So I think this is pretty cool, and that there's nothing else to it. Now all you have to do is just go to here and then get this data and plot it against CPCL. Oh, sorry, CL versus alpha. So, and then I think the question also asks you to plot the XCP, the location of center of pressure with respect to alpha. So that's you have this right here, and if you open your text file, you'll also see the XCP variation, right? All you need to do is plot XCP as a function of alpha, and that's all, and see what the trend is. So I think this homework kind of makes a good segue to what happens in cambered airfoil for location of center of pressure. So we'll talk about that in the next class, but this is pretty much all you have to do for your homework 9 problem 1.2. So let me know if everything works okay. I haven't used Xfoil, but Xfoil you already have practiced using Xfoil in homework 2, right? So if anything comes up, just let me know. So until then, bye-bye.